Yeah. Hold on.
What? I'm not holding on. This is on the internet. Go.
No, we don't want it.
Alright, so we did the speed of sound. We tried to calculate the speed of sound using the Doppler effect. So, our purpose.
So the purpose was to calculate our experimental speed of sound using the formulas of the Doppler effect. We used two cases of the Doppler effect. One of them was a moving observer and the other one was a moving source. We didn't did the general case because it would require at least 3 people in our lab. So, but we did derivations later. So each case had 2 directions, toward the source and away from the source for the case of moving observer, and for the case of moving source we had a spinning thing which made the constant frequencies, and we did it toward. We calculated as a toward because its frequency was higher than its initial frequency. So, alright, that was the purpose.
Alright, these are.
Alright, so the moving observer toward the stationary source, the formula f prime equals f over 1 plus u divided by v, where u is the speed of observer, v is our speed of sound, which we try to calculate, and f is the initial frequency. Now the moving source. So the observer is staying stationary, and was a moving source. We had, as I said, we had a rope, and with a source, and we calculated its period using Pro. And we measured its radius, so we was able to measure its speed, and plugged into the formula for u.
Alright, so derived for v, u is speed of the observer, and actually what we had was the Logger Pro and the microphone, like a motion sensor. That way we could accurately record the frequency at a certain point and velocity, so we had spinning around. So let's say Mr. Vini's hand was the thing, so we had it spinning at that point, and that's how we configured it.
Alright, now. General case.
We didn't do general case, but that's basically the observer's moving at a certain speed, and so is the listener, and they're going either towards or away, and that's how you calculate frequency prime.
And we did the derivation, and we found that if you make if you use the same frequency for calculating the frequency prime for observer and for the moving source, you can derive the equation, which will give you opportunity not to calculate f prime. So you can calculate speed of sound without knowing f prime for general case if you calculate those for 2 previous cases.
Alright, here are derivations. Speed listening going towards source. Oh, also for the spinning thing, we had to get the angular velocity because we only have periods, so we had to find out a way to do that. So we eventually found out, well, we just looked in the book, that tangential velocity is equal to 2 times pi times the radius over the period. So we did radius of the spinning. Alright, here's some graphs we have. We actually got really close to the speed of sound, in my opinion. For this graph, which was the velocity moving away, the source moving away from the source, the listener moving away from the source, our slope actually got to be 318.6 meters a second, and
What are the axes? Can't see it if you.
u, on the y-axis we have u, which is the velocity, speed of sound, well, speed of observer, and on the x-axis we have f prime over f plus 1, which is just the part of the equation that you need to get. This is velocity going towards the source, which was 306.6 meters a second, still really close to the experimental value. And then here is the moving source towards the observer at rest. We were able to get to 359.1 meters a second, for the speed of sound, which is really, really close to 343.
Then we also calculated the accepted value. We used the equation that says when the temperature equals 0, the speed of sound equals 321 meters per second. And for every 1 degree increase in temperature, the speed of sound increases by 0.6 multiplied by the temperature increase. So this was our accepted value, and then we did error analysis through each graph and calculate our error.
And this is actually setup version number 3. We used to actually have the cards, so we had a card going through the thing. I thought it was a great idea because it was going to be super accurate, but the cards moved too slowly to get a significant frequency change. So we ended up with the scanner running towards the thing, and we had the speakers with each frequency.
I tried to run in a constant speed, so I took a distance far away from the source to kind of rearrange my flow.
So we did the distance was really basically the range of how far that velocity thing can sensor. And there's the trusty old laptop. And thank you.
Very good. We have time for one question. Just one question.
We're not up to the pressure of one question.
When does the movie come out?
Next year.
Good work, guys.